my speech will be about the restoration of skeletal muscle through the use of functionalized biomaterials. So, in vitro model are gold standard to investigate cells and tissue. From the first in vitro model, many revolution and evolution of this methodical have been made so far, as it is a simple and realistic method. Therefore, choosing an appropriate in vitro model could ameliorate the final goal of our experiment, such as proper cell growth and tissue formation. We are in particular interested that the skeletal muscle has, as we know, the skeletal muscle tissue loss is considered to be irreversible due to the low regenerative ability of this tissue and limited therapeutic options that are available right nowadays. In order to restore the skeletal muscle tissue in vitro, we decide to engineering the skeletal muscle by the use of a scaffold, so a support that is different from the conventional tissue culture plastic. The scaffold is one of the three main components of the tissue engineering. The tissue engineering is an innovative field. There is a branch of the regenerative medicine and is composed of biomaterials or scaffold, as we decide to use. The use of cells, in our case, myoblast cell line, and the addition of regulatory signals, for example, growth factors. In order to develop a scaffold, we use the electrospinning technique. That is a fiber spinning technique widely used in the field of tissue engineering, as it is a very cheap and easy technique. It is a fiber spinning technique, so the process starts with the selection of a polymer, and in our case we decide to use the PLCL. It means polylactic acid and copolycaprolactone. It is a copolymer which has mechanical, physical, and biological properties tailored for skeletal muscle application. So once we have the polymer solution, it is charged in a glass syringe, fixed in a syringe pump, that is connected by a voltage source to a drum connector. So once the pump pushes out the polymer solution, the jet is spread out from the needle of the glass syringe and is attracted by the drum collector. So the polymer, now in nanofiber size, wrap around the drum collector because it has a high-speed rotation. So it forms at the end a matrix, so this electrospan net composed of nanofibers. In order to reach the best results using this technique, we have to manage three variables. So the polymer solution, the setup of the instrument, and the environment. So why we decide to use the PLCL? Because, as I said before, it has, looking from literature, a good mechanical, physical, and biological features suitable for biomedical application, because it takes advantage from the PLA, that is a polymer with low degradation rate, and so suitable for biomedical experiments, and by PCL, that instead has elastomeric properties that counteracts the high rigidity of the PLA, and so make possible the muscle functionality, so make possible the muscle contractility. So once we develop the PLCL scaffold, we fix it in an insert, and we culture on them the C2, C12 myoblast murine cell line. And in the same time, we have a control consisting of the C2, C12 seated on tissue culture plastic. So in order to examine the biocompatibility of our chosen material, we made a cell viability test for 1 week. We didn't observe difference of C2, C2 have cell viability on scaffold and on the conventional tissue culture plastic till 5 days, where at day 7 we have a difference, but is not related to the biocompatibility of our scaffold, but is related to the fact that the cell viability is indeed coupled with cell proliferation, but is uncoupled with cell differentiation. And in our case, our scaffold acts as a stimuli for the cell differentiation. So this is why we had at day 7 a reducing number of cells on our scaffold. Indeed, in order to confirm again the biocompatibility of our chosen material, we performed the scanning electron microscope to look at the cell morphology. So we seeded our cells on the scaffold, then we look at them after 2 hours. And in our 2 hours, we have the first phase of the cell attachment, where C2, C12 here, as shown in the figure, are with a spheroid shape due to the previous trypsinization. And then in 6 hours, the cells start to elongate in trying to reach their natural morphology, so they are completely adhered on our scaffold. And interestingly, in 24 hours, we observe well-elongated cells, and the elongation followed the nanofiber direction. So from this first analysis, we got 2 results. The first results confirmed the biocompatibility because we couldn't observe any difference in morphology of our cells. And secondary, we proved the importance of a unidirectional fiber orientation during cell morphogenesis. So we move our attention from the cell proliferation to the cell differentiation. And our C2, C12 seeded on our scaffold were stimulated toward myogenic process by culturing them in a specific differentiation growth media. And we made a control, so the C2, C12 were kept in a growth media. We investigated the timeline of the myogenesis process, and we focused our attention on crucial time points. So 1 day after the induction of our C2, C12 seeded on our scaffold and our control, 5 days and 10 days. So again, we performed scanning electron microscope to look at them. So in our control, that consists of the C2, C12 seeded on our scaffold and kept in a growth media, we could confirm the importance of leaving an unidirectional orientation of the fiber that guarantees the cell orientation and allows cell interaction and cell-cell additions. Indeed, 1 day after the stimulation, we detect the cell-cell additions. So it appears that cells are trying to call in each other, and probably this addition could promote the activation of inner signaling pathways that are important for the secretion of cytokines, and so make possible migration and differentiation with protein synthesis. Indeed, looking at the literature, it is reported that mechanisms through which such addition triggers the fusion are not well understood. And as follows, at day 5th till the last day that we assist our scanning electron microscopes on 10 days, we have fused myocytes and well-organized myotubes. Surprisingly, we couldn't observe cell-cell addition. So we have a decline of cell-cell addition once the cells start to fuse each other. Indeed, large size in myotubes were still observed at day 7, and they keep stable till the 10 days. So collectively, our data show that the alignment of our design scaffold has a role not only during the cell morphogenesis, but moreover influence, thanks to the development of this cell-cell addition, the bioactivity of the C2C12 that is fundamental for myoblast fusion and myotubes formation. And so we also analyzed the protein expression during the myogenesis of the C2C12 either on our scaffold and on our control. Again, we look at different markers throughout the myogenesis process. So we have an early marker, the MyoD, and as the Western blotting analysis showed, we have difference in the expression of the MyoD. That seems to be later expressed in our scaffold compared to control. This is, of course, given by the presence of a scaffold that has an influence on the cell behavior. Indeed, also the myosin heavy chain has a difference in the expression of the C2C12 either on our scaffold and our control. But even we hardly define the myosin heavy chain expression by Western blotting. It was clear by the confocal imaging the expression of the myosin on our C2C12 seated on a scaffold. Indeed, as shown by confocal imaging, in our control, so time 0, in which cells are kept in a growth media, so we expect the cells are not committed yet, we observe the expression of the myosin that is indeed a late marker and usually expressed in the late phase of the myogenesis. So even at time 0, we observe some positive cells of the myosin heavy chain. And the stain of the myosin steadily increased over time, reaching its peak at day 5, where we observed our well-formed myotubes that are kept stable till day 7. So here I want to show how the myogenesis is indeed different just by the presence of a scaffold, and how the scaffold as a booster, so enhance the myogenesis and make possible the differentiation of the C2C12. Of course, changes in protein expression are related to changes in gene expression. So we look at gene transcript level of C2C12. Again, we analyze some early and late genes. This is a work in progress, so it needs further analysis. But of course, we could detect some difference in the trend of genes on our scaffold, so even C2C12 scaffold and controls. So that means that ever a scaffold as a support that is different from the normal tissue culture plastic reflects on different behavior of the cells that is related to different gene and protein expressions. In overall, these preliminary data suggest that aligned and elastic nanofibers facilitate the C2C12 organization, as shown by the scanning electron microscope imaging, and it reflects in a different gene and protein expressions. So the PRCL, so this scaffold that was designed by us, enhanced the myocytes differentiation because promotes cell-cell interaction and cell-cell addition and fusion and maintenance myotubes. So I could suggest the use of this scaffold as is stable at 37 degrees, so suitable for biomedical application. And it could be useful for further analysis without animal testing, so animal-free experiment, as it is biocompatible and is ready to use. So the tissue engineering aimed to skeletal muscle tissue restoration through the use of scaffold, that in our case was obtained by the electrospinning technique, acts as a booster for the myoblast differentiation and overcomes many obstacles and limitations given by the normal tissue culture plastic. Thank you for the attention.
So, thank you very much for this interesting perspective. Are there questions from the audience? Mm-hmm.
Yes, we made, yeah. Yes, we look at modulus. Yes, we are indeed, we are going to do other experiment about the mechanotransduction. So we are trying to stretch our material and look what happens in the cell. We expect to have an increase, not in a number of cells, but mainly in a differentiation, so difference in pathways, so gene and protein expression. You're welcome.
Further questions? I have one. How is this practical perspective, this BLCL is not biodegradable, as if I understood right? How is it in clinics? This would stay forever and not change the supporting properties to inhibiting ones?
So it's biocompatible materials, so it's biomaterials, and we decide to use these copolymers, so made of these two polymers. So we have the PLLA that has a low degradation rate, but is biodegradable over time. So it's stable to 6 months. So we have the time necessary for skeletal muscle restoration because it permits the skeletal muscle growth and then the formation of the tissue. So it's proper time.
But you have not tested yet till when it disappears? The time was too long.
These data are already have been tested, so they come from literature because it is a material that is widely used and commonly used in the field of regenerative medicine and tissue engineering.